I'll start off by reading the question and drawing the diagram. So let me just draw. So I have a monochromatic light source of 495 nanometers, that's the wavelength, and it is incident normally on a grating. So for this grating, we know that it has 500 lines per millimeter, so that allows me to find the value of D, but I'm just going to write down that value of N, that's my N, and that is 500 lines per millimeter. In our diffraction grating equation, we know d sine theta equals to n lambda, correct? So that actually allows me to find my d. And from that information, I know that d is equals to 1 over n. So I'm just going to write it down as I read. I'm asked to find how many diffraction lines can be observed theoretically on the screen. So there is actually a screen. I'm going to draw it a bit longer. And there's a screen. And we want to know how many lines can be observed on the screen, theoretically. So what's going to happen to the light after passing through the grating? After passing through the grating, we will have the 0th order down here. Then, of course, we will have our first diffraction line, which is our n equals to 1. And then we will have our n equals to 2. Then we'll have our n equals to 3, possibly, and so on and so forth. So to know how many lines can be observed on the screen, we need to know what is the maximum order we can actually observe. Alright, so you'll go on and on. What's the maximum order we can observe? From this equation, therefore, what is your limit to the maximum order? You realize that your sine theta, the angular displacement of the maximum order, is actually 90 degrees. That happens at this case. Of course, some of you may be saying that, hey, my screen is flat. How is it ever possible to be 90 degrees? So we can imagine either the screen to be infinitely long, or alternatively, instead of having a flat screen like this, we can have actually a circular screen. So if you have a circular screen, then yes, you are able to capture all the diffraction patterns. Alright? So that is actually the crux for solving for maximum order and therefore the number of diffraction lines. So this is what we are going to do. For maximum order, I'm going to call it n max, then theta is actually 90 degrees. So substituting that into d, sine theta equals to n lambda. Remember, I need my d. And what is my value of d? My d is 500 lines per millimeter. So I'm just going to do it at the side. D is 1 over 500 lines per millimeter. So it's 1 over 500 millimeter. And it's 1 over 500 times 10 to the power minus 3 meters. So substituting that, then what we want also is n. Then we'll have d sine 90 degree equals to n max times lambda. N max is what I want. So it will be d. Sine 90 is 1. So I'm going to keep it as 1 over lambda. Lambda is 495 times 10 to the power of minus 9. So put it in. 1 over 500 times 10 to the power minus 3 over 495 times 10 to the power minus 9. Put this into a calculator. You should get something like 4.04. Now remember, in terms of number of orders, is always an integer number. So what this value says that the maximum order I can get is 4. It has never reached 5. So I need to round down. After that, because it's an integer value, and therefore my n max is equals to 4. Okay? And with that, we can therefore know that the maximum order I can observe is actually 4. But the question asks for the number of diffraction lines. So this goes back to the pattern. We need to consider the 0th order at the center. And then if there's n equals to 1, then there's actually 1 on each side. So if there's n equals to 4, so I need to go 1, 2, 3, and maybe the 4th one. Okay, n equals to 4, 4 on each side. And so therefore the maximum number of diffraction line, because of the symmetry, we will have 4 orders, and each order can have 2 diffraction line plus the 1 which correspond to the 0th order, and that will give me 8 plus 1, and that is 9. So this is my answer.